Hello everybody, welcome to the second part of our introduction to the Building Scalable Distributed Systems course. In the first part we talked about how systems had evolved to become distributed at massive scale, based in part on the growth of the internet and the business opportunities that it created. In this module we're going to briefly look at the challenges to building systems that this evolution has created. So just to give you an idea of some of the loads that contemporary internet-based systems see. Amazon, 175 million unique visits a month. You can read these as quickly as I can say them. And what's interesting about these numbers is they're guaranteed to be wrong, as it says at the bottom. Why is that? Well, simply because these systems evolve daily, by the hour. And the numbers we see published in reports are typically months or even years old. A lot of this, again, is commercial in confidence. So we can only get estimates from this, but as you can see, these numbers are pretty big. 175 million unique visits a month to the Amazon retail site is a lot of visits. Work out how many of those how many that is per second, and you'll get an idea of the load we need to process. So we have high traffic. Consider ad exchanges a real dark corner of the world of technology to most people. But when you do a Google search, for example, Google decides which ads to place in the results page. And to do this, they use ad exchanges, which have to handle like 1 million requests a second with guaranteed latencies, so that the search is not slowed down by choosing an ad. These systems use huge volumes of data. Terabytes used to be big, but now petabytes are pretty common, and exabytes are not uncommon at all. Gmail, for example, is a many exabytes data store. And of course, these systems, they process huge amount of data, but they need to do it quickly. You're not going to use a site that takes 20 minutes to respond to a request to browse the catalog. You need fast response time, and this response time needs to be provided to potentially millions of people at exactly the same time. And of course, you need security, and you need reliable systems so people will come back and know that they're going to get a good quality of service when they come back to your site. And from an engineering perspective, you've got to think about compute costs. And the challenges, all these challenges mount up to make these systems extremely complex to build. You have strict latency, massive throughput, deal with data securely, and need to be available 24/7. It's very, very rare when Netflix goes down or Amazon goes down or Google search goes down. So availability is a key factor for these systems. And again, we need to do it in a cost-effective manner. Look at the costs. These systems typically run in very large data centers, and the cost of a typical data center comprise the numbers on the slide here: 57% servers, 31% power, networking 8%, and others such as people and building costs 4%. So 88% of your cost for running a system is impacted by data center costs. If you can reduce this amount, so say you can reduce the amount of servers you're using by 20% by making your code more efficient or your database access more efficient, then you can reduce the amount of cost that your system accrues. And if your system's running on 10 servers, then dropping it to 9 or 8 servers probably isn't a big deal. But if your system's running on 100,000 servers, dropping that by 10 or 15% is a significant cost saving. So many of you have been taught that optimization is really a second order problem in software development, software engineering. At this scale, it's not. Optimization results in cost savings, and small cost savings at this scale can result in very large dollar amounts. Response time is a very important factor of any scalable system. There's been many studies that show that small increases in response time, as the example on the slide here says, going from 0.4 of a second to 0.9 of a second for Google, decreased traffic and ad revenues by 20%. So if you can provide a very consistent, fast response time, as Google and Amazon and co typically do, then you're going to increase the revenues, increase the amount of traffic and the revenues it generates. And of course, some systems, such as ad exchanges, are contracted to provide responses within certain latencies. So response time is a crucial issue, and it's one that we'll spend a fair bit of time studying in this course. Isn't an example of what's called a long tail response time? So here you can see that the number of requests being processed quickly is very, very high, less than a second. So we're getting 18,000 requests processed in less than a second, and about half that, just over half that, processed in less than 2 seconds. And by less than 4 seconds, which again isn't too long, the majority of all the requests are being processed. There's still a number at 5, 6, 7, 8 and greater than 10, but you know, it's not that many. However, it's still a significant percentage. I'm guessing 15% maybe. If you're part of that 15% where you're experiencing 10% response times, then you may not come back to this site. And hence, systems typically don't want to give people this long tail response time behavior. They want to have response times guaranteed to be less than a second or two, so that nobody is hanging around waiting and potentially thinking, I don't want to use this service no more, I'm going to use a competitor. And we'll look again at techniques in this course that are used to enable you to provide very high guarantees of response times within certain latencies. So it's pretty obvious, hopefully, that internet scale systems need to be able to handle massive throughput, i.e. thousands of concurrent requests. Imagine Christmas sales on Amazon, or a new release of a movie on Netflix. This creates spikes in load, but significantly increase the throughput that needs to be handled. And if you fail during this time, then you're going to lose money, and you're going to have customers dissatisfied and potentially not come back to your service. And that's not really an option. We really need to provide very high throughput systems with guaranteed low response times. Here's a graph of just a very simple graph of throughput plotted against the number of users and transactions per second. As you can see, typically as the number of users grows up to about 150 in this case, the amount of transactions is steady, and from about 150 onwards. So we can still handle 350 users plus, but obviously if you think about it, that means that they're going to be getting longer response times. So this is a very typical graph for a single server, and it's one that does not guarantee low response times, in response to increased throughput. And again, we'll look at techniques in this course where we can basically allow the throughput to increase as the number of users increases, instead of flattening out as it does in this graph. And basically the techniques we're talking about use scale out, or horizontal scaling. And as Wikipedia says, this means to add more nodes to a system. Equally important, you might want to scale out. Say you handle a spike in traffic, the release of a new movie on Netflix, and after 2 days people are bored and don't want to watch that no more, and the traffic goes back to normal levels. You don't want to keep the increased resources that you needed for the new movie available and costing you money. You want to shed those. So it's equally important to be able to scale down your system from the capacity that you have for handling high loads. So scalability and typically scaling out is what we'll talk about a lot in this. Scale out is basically the technique used to create highly available systems. If we have single points of failure, such as a single machine, then it will fail at some stage. The disk will fail, the power will fail, the network will fail, and we'll lose our system. It won't be available anymore. So the typical technique is to scale out your system to make it more fault tolerant, because at scale everything will break. So we reduce all of the single points of failures in our system so that when single nodes or components fail, others can take their place without affecting the user traffic. Just as an example, if I'm running a system on 10,000 different nodes, each with its own disk, these disks crash every so often. So how many disk crashes might my system experience a year? Have a think for a minute. What information do I actually need to estimate this number? I have 10,000 disks. How many will fail each year? Basically, we need to know the annualized failure rate, and the equation for that is given on the slide here. And from experimentation, a common drive has about 300,000 hours mean time between failure. So on average, a disk will fail every 300,000 hours. So if you put that number into the equation at the top, you get a 2.92 annualized failure rate for disks. So that means that any of my 10,000 disks in my example might fail every year with a likelihood of 2.92. So basically 3% of my disks are going to fail every year. And this was enforced by a study from CMU, which showed approximately 3% mean AFR over 3 to 5 years. So you can do the math. In 10,000 nodes, 3% of those will fail every year. I'm going to have to write my system to be able to handle those random failures so that they don't affect user traffic. When I make a system highly available, I typically have to replicate the data. I have to have multiple copies of the data. So if one copy is unavailable, then another copy can be accessed by the transactions. And this creates a problem known as consistency. When I make an update to replicated data, I have to somehow make sure that all of the copies get updated. And this isn't always simple because I may not be able to see all of those copies at exactly the same time. This occurs when you perhaps get something called a network partition, where part of my system is not visible. My system has been partitioned by a network failure. So consistency is a major problem in highly scalable distributed systems, and one which we have to engineer our systems to handle. And it's again a topic that we will spend a considerable amount of time thinking about in this course. Now we need available systems, we need really fast, responsive systems that scale. We need to be able to handle consistency, we need to make the data secure. We need everything, but this is engineering and we can't build the perfect system. There's just no one holy grail solution for building these systems. If we increase consistency, we probably affect our availability. And so every decision that we make has a trade-off. And part of this course is to teach that as engineers, you need to be able to understand the implications of the decisions you make. Every decision you make will have benefits, and it will also have some downsides. And the trick of building these systems is to maximize the benefits to suit your business needs and minimize the downsides so that they don't, when they do occur, they don't massively affect your business. So being able to make design trade-offs is a key skill in this area. So massive scale systems are the way we build technologies now that run on the internet. And we need to satisfy the functional requirements. We need to do what the business wants to make money. We also need to satisfy the non-functional or systemic requirements, because without satisfying these, without providing fast, scalable, secure systems, the system will fail. And that's really what this course is about. We'll talk about the theory and practical knowledge needed to engineer robust, scalable and efficient internet scale systems. We'll do this by having some recommended reading each week, some lectures such as this online, and there will be 6 or 7 quizzes that are graded throughout the course. We'll also have some practical exercises which we do in between lectures in class, and 4 projects which build an increasingly scalable high throughput system. And of course these are graded. And it's just a list of topics that we will study. This isn't comprehensive, but it gives you an idea of the flavour of the course. We're talking about modern scalable information systems for systems that you're using every day on the internet. And we'll talk about the systemic qualities, the availability, performance, scalability, etc. that are needed to build these systems, how they need to handle consistency, some of the theory behind consistency and state management, and then we'll talk about concurrency, distributed systems, transactions, and the sort of middleware technologies that are needed to build these systems. You don't build everything from scratch, it's far too complicated. And then eventually we'll look at some scalable analytic technologies such as Hadoop and Spark, and finish by looking at cloud-based systems.